So welcome everyone for Cloud Computing and Big Data. Today we have lecture 11. It's my pleasure to invite one of my postdoc researchers, Chadi Barakat, here to give you a lecture because he's really a practitioner in big data analytics and cloud data mining. So welcome, Chadi. How are you today?
Yeah, thanks, Morris. I'm doing well. It's an interesting time to be doing this kind of work in cloud computing, big data, machine learning, all of it. It's a very exciting time for all of this stuff, and I'm excited to give this course today.
Excellent. Yeah, so I mean, you have been doing a PhD here in the course at the University of Iceland, and basically you would be also hopefully a little bit, an angle here for some of you from the students that want to also do a postdoc or basically some PhD. And I would recommend you then also to talk to Shadi, maybe not as part of the lecture today, but of course then in subsequent emails or so. But yeah, before we go maybe in the material of Shadi's lecture today, let us maybe quickly review what we had the last time. So if you remember, lecture 10 was really then building on top of lecture 8 in terms of infrastructure as a service and lecture 9 in terms of platform as a service, integrating all together really to a software running really, or basically ready to run software where you swipe the credit card and you have a very nice, let's say, application experiences with have here. And there are some interesting benefits if you do it in the cloud, right? One was the idea of this horizontal scalability that you discussed, because in a way your infrastructure is so scalable on both sides, on the infrastructure as a service, but then also with these components you build your solution from on the PAAS level, so that you basically can grow with a number of users, with a number of data sets of data that you accumulate over the years or so, where you, for instance, use your app. And this is, of course, something which is quite nice. We have seen Angry Birds as an example, exploding basically in the number of users. And when you then have a virtualized infrastructure with PAAS and IAAS components, your software as a service solution is really high quality and will enable, of course, that even more users want it. And then we put the emphasis a little bit on some of the SaaS solutions we either already had here in the course discussed, like the Google Docs, enabling us, let's say, edits all together jointly on a document at the same time. So this is really also one advantage of this clouds. And then, of course, also the Amazon SageMaker that is currently part of your assignment, or basically that we had also in earlier lecture when we talk about machine learning. So there was one specific field, or two if you want. One was the customer relationship management, and the other one was the ERP system, the enterprise resource planning, because they are somewhat special because they're quite a huge area where cloud solutions have been extremely successful, where we talked about millions in the market. And we had here the example, for instance, from Freshworks here, this Fresh Sales, where you really can understand your customer inside out. It had links to social media. With one click, you see all the Facebook profiles, LinkedIn profiles, all the information about the customer. You can, of course, track different interactions with your team, like phone calls or emails, and share them across, let's say, your team within the company. And then we have even seen that more modules can be added, right? This kind of cross-selling idea that you start maybe with a specific element like managing your customers, then it turns out to be more a sales component you add. So you have leads and they're progressing to the sales pitches, to the real actual sale of your component or your product, whatever it is you do. And then you see even here, as one example, the sales forecasting done smarter. We see again that AI, artificial intelligence, deep learning, machine learning has also a bigger impact now in cloud computing all over the way. You have seen already AI solutions are integrated basically all the time now in all of this, let's say, more internet-based or online-based services. And this is really the nice idea of software as a service. If you want, remember, it is also based on a scalable platform below. But I think that's all I wanted to recap maybe of lecture 11. Maybe the next slide, you will see, Shadi, that and the others here in the course, that we will dive now a little bit more again in practical topics. Practical also in the sense that some of them are related to your assignment 3, the final assignment. And you have really with Chadi someone who did this himself during his PhD here at the University of Iceland. So he's really an expert in big data analytics and cloud data mining. And that's is therefore my pleasure that he will also talk today in the course. And yeah, Shadi, take it from here.
Okay, so thanks for that, Morris. Um, Before we carry on, I think it would be a good idea to go to have an outline of what this lesson is going to be about, but also to give a short introduction of myself. So like Morris mentioned, I did my PhD at the University of Iceland. My PhD was in bioengineering, but the thesis itself focused on applying machine learning and big data analytics applications on medical applications. So there was some analysis of medical data, some prediction on medical conditions, given some clinical information that we got from clinical partners or that we had to collect from all over the internet. So hopefully I'll be able to mention about my experience in that field in the second part of the lesson here. But mostly in the first part, I'll talk about something that was a significant aspect of my PhD, at least in the first year, where I worked on some association rule mining, which is an unsupervised learning method for big data. So the outline then is about association rule mining with big data, where we also break down the application that I did in the on for off project, and then talk about the different applications of association rule mining. And then in the next part of the lesson, we go through data mining and deep learning for healthcare. There are two applications in that part, and we'll go into details for both of them. So let's move on. Association rule mining sounds like a very broad term here, but it's mostly applied everywhere you go on the internet. So it's this thing where if you buy something off Amazon, for example, or any online marketplace, and then a couple of days later you go on that website and they recommend something that you actually do want, or something that you may not want, but it is similar to the thing that you already bought. It's users who bought this frequently also buy that. This is a way for systems to develop a relationship with the customer, but also to try to predict future sales. So these are commonly referred to as association rules, and mining these rules is based on developing a number of frequent item sets. Item sets are these items that are frequently bought together. So these rules that we are mining in this case are which item sets are frequently bought together, which make sense, and which can be used to predict certain user behavior or customer behaviors. Some of them are very generalistic, which apply to a general population, and some of them are more specific, which we won't go into with much detail here, but they are more personalized recommendations. This approach, association rule mining, is unsupervised, as I mentioned before, meaning that we don't give it a specific goal. If we do some kind of machine learning here, there is no end goal that we specify for the algorithm. The algorithm looks at all of the data and comes up with mathematical answers that some of which might be interesting to us, some of which not at all. And that's going to be a key part of the next couple of slides. There are several algorithms that help us perform association rule mining. For example, a priori and FP growth will be part of the lesson today. I don't go much into detail with Mafia because I didn't have experience with it, but there are a lot of algorithms, some of which perform better, some of which perform worse, depending on the application that you're going for. So this is also a common aspect of all of this lesson, which is that you need to know what kind of application you're going for, and based on that, you know which application, which implementation works for it. So let's move on to how association rule mining works. And here on the right side, we have a very basic dummy example that you'll find in most books about association rules, which is just a list of items purchased from a supermarket. So you have one basket, and then another, etc. From these items, we can easily extract, or a basic algorithm will extract that diapers and beer are often bought together. So, if somebody buys diapers, usually it's a good idea to recommend that they also buy beer. And in the real world, this is a parenthesis here. In the real world, this makes sense because usually parents who often go to a bar, whenever they have a new baby, they aren't going to go to a bar, and so they drink at home. So it would make sense that people who buy diapers often buy beer. Um, so based on these recurring purchases, one can develop the idea that there is a strong relationship between diapers and beer, and based on that, um, that we can say that this is a frequent item set. The challenge here is that sometimes these transactions are in the billions. For example, Amazon. There are billions of sales happening every day with varying numbers of articles. If you have, let's say, 100,000 items 10,000 items being sold and 100,000 transactions, then you have a list of in the billions of possible interactions, possible combinations of items that you can suggest. You need you have a lot of data and you need a lot of processing power to be able to go through this data and weed out whatever is irrelevant to your application and pick specifically the ones that you care about. So in this case, automation is very necessary, and that's why we develop algorithms for these association rules. But also, it requires that these algorithms that you use, that you implement in this case, are efficient. This is one of the main goals of the On4Off project that I worked on between 2020 and 2021. This is specifically during the COVID pandemic, where it was necessary that brick and mortar shops slowly transition into selling their stuff online. And it would make sense in this case that we start off on the right foot here and immediately have them have the best way to recommend to potential customers what articles they have. So there are large quantities of data accumulated in the databases of these retailers that haven't been used in ages, but they give us a long history of what the customers are buying from this specific retailer and what kind of products they sell. In this case, these are retailers who sell perfumes, who sell beauty products, who also like related stuff to beauty products. And so since they are sitting on this data, it would make sense. This is an environment that is rife with information that can be used for association rule mining. So it was a perfect application. So these purchase data that are collected on a daily basis were accumulated over 10 years, if I remember correctly. And they were labeled, and the people from the project also helped us out by telling us what kind of sales make sense and what kind don't. Because also what we didn't know starting off with this project was that discounts, bargains, seasonal um, rebates, and all of that, they are also counted as transactions. So we had to do a lot of cleaning with these people. And to be very honest from the beginning, association rule mining also requires a lot of understanding of your data. You have to understand how your data points connect one to the other, but also what you can exclude in this research. So there are a lot of things that can be gained from this application because one, it encourages the customer to stay longer at that retailer, to buy more, to find the things that they need. How many times, for example, have you been on a website where you're looking for the thing that you need, but you never find it, and you buy one thing, for example, you buy a new tablet, and you want to find a cover for that tablet, but there is no way for the website to recommend this for you. You can't find it using their search. In that case, this is where this association rule mining work might help. And at the same time, for the retailers themselves, it improves their business. It makes them more accessible, more reachable. So one of the algorithms, as I mentioned before, is called the a priori algorithm, where all of these association rules, all of these transactions are collected, and the algorithm goes through them one by one. It builds a list of all of the items, as you can see here, and counts how many of them, how many times each of them appears. This count here is compared to a minimum support value mentioned here. This minimum support value can be tuned, which is the job of the person doing the machine learning here. By tuning this minimum support value, you weed out the items that are not that frequent. So in this case, cola and eggs are not that, they don't appear that often in these transactions. Whereas milk, diapers, bread, and beer are quite common items. Based on this collection of items of frequent one-item sets, the algorithm does a second pass through the transactions and collects the relationship between this item and every other item in the list. And then it compares that count of the two item sets, how many times they appear versus the same minimum support. And based on that, it removes the items that do not reach this minimum support, and then it moves on to a third iteration and a fourth, etc., 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 until there are no more item sets to be built. Based on, as you can see from how I'm explaining this, this is a very time-consuming and a very resource-consuming process. But it is the most commonly used algorithm for association rule mining because it's such a simple algorithm. Unfortunately, as we'll see in the next slide, it doesn't scale very well. So generating these frequent item sets, and here, for example, we have an output from our approach. These item sets are then used to build a one-hot encoded matrix where the relationship of every item with every other item is compared as a binary relationship. And based on that, the association rules are generated, and again, another support value is set for these association rules so that they can be weeded out, also the ones that don't make sense, the ones that don't have enough confidence or support, as you can see here. And then based on these values, we can come back to the retailer and tell them that, yeah, usually people who buy Chanel are also interested in, people who buy Hugo Boss, Clinique, Rituals, Dior are also probably interested in Chanel products or Armani products, for example. And this is This is useful, honestly, for the retailer. One person, one salesperson at the store might know some connection between one and the other of these products, but there is no way for them to know all of them. Applying this association rule mining algorithm in your code, if you use Python, for example, is very easy using the MLextend library, which is available on the Python repositories. And it's very easy to implement and it's very easy to just run out of the box. All you have to do is just understand what inputs you're giving, what outputs you're expecting, and also to tune based on your understanding of the data itself. The tuning you can do in this case is how much support you want your frequent item sets to have, how much support you want your association rules to have, and you can also select one of these four other parameters to define the quality of your prediction of an association rule. It's either confidence, lift, leverage, or conviction. I won't go into the details of what these values are, but they are mathematical calculations or statistic or probabilistic calculations of over your association rules. So, like I said before, a priori doesn't scale up very well. It's mostly because of all of these recursive passes through the data. So for a relatively small number of transactions, this is feasible. But if you have large scale transactions from where it's not just a relationship between the retailer and the customer, it's more a relationship between a major retailer and smaller retailers as a provider or producer or a major company that has more than one type of product that they develop. In this case, you're dealing with the billions or much larger scale of products being sold. And in this case, a priori is probably not the best approach. You might be able to parallelize it and scale it up a bit, but there is a limit to how far you can get this, how far you can accelerate this without losing a lot of resource. And as you saw in the previous courses, previous lessons, having access to cloud resources, having access to cloud computing is expensive. So your main task here is not just to produce good association rules, but also to produce rules that are also cheap. So you don't lose money trying to develop these rules. So the main idea is to take into consideration the computation cost when planning your machine learning approach, because a priori is probably not the best approach here. A similar approach to association rule mining, but which is more efficient, is FP growth. It has a radically different implementation, but the results are very similar, and the accuracy of these results is also very similar. FP growth, instead of doing multiple passes through the data, only does two passes. The first one is to develop the unique items, to build a list of all of the unique items. And the second one is to build something called the frequent pattern tree. The frequent pattern tree here relates all of the products to each other without having to have um, too many repetitions. And then after that, the idea of collecting all of the frequent item sets is just as simple as going down that tree from top to bottom and then seeing how many times you have items that start with, for example, here, A, D, and E, A, C, D, and E, etc. So as you can see here, this is radically faster than a priori. And this reduction of computation is money in your pocket. It reduces your costs, but it reduces the headache of in case you make a mistake or you have to run this another time with higher support or lower support, you don't lose too much time, you don't lose too much, let's say it outwards, you don't lose too much money trying to figure out something that can easily be done with this algorithm. So this approach allows you to directly extract these association rules and to make it very efficient. This is obvious in this slide here, where you can see that running a priori versus FP growth, in all of the trials, on average, FP growth is much faster than a priori. And these are two implementations of a priori, one with low memory and one with high memory, with normal memory. And neither of them come close to how quick FP growth performs the task at hand. Similarly, you can see with increasing number of transactions, the a priori algorithm is taking much longer, whereas FP growth is growing. It does eventually take more time because it still has to build the one-hot encoded matrix, but that's also a thing that can be resolved. But at the same time, it still takes significantly less time. The scale up for this algorithm is much easier than the scale up for a priori. Moving on, these algorithms are so established in the industry that they are part of the IBM Cloud Pak for data. It is built into the model as association rules. You can see it here. And this is something that you guys will probably go through in the next implementation with the Singularity or Docker containers. But mostly you can see that there is a cloud implementation of this because people want to apply this without having to move the data around between different servers. If there is a cloud resource for applying this algorithm, let's just do it. This is another example of how this is implemented and how you can set up the pipeline for this. And I guess this is just another implementation of FP growth on Apache Spark. All in all, here it's mostly that these algorithms are well established in the industry, and it makes sense here to understand what you're trying to do with your data. It makes sense also to implement it in a way that is efficient given the amount of data that you have, but also efficient given the amount of computational resources that you have. There is a financial benefit for these companies to host on their cloud computing resources these algorithms. And there is an incentive for you as a machine learning practitioner in this case to use these resources efficiently and to also provide good results for your customers. So with that in mind, we get to the end of the first part of the lesson where we talked about applying association rules for extracting association rules from transactional data, from shopping carts, and a real-world example that we implemented in the On for Off project. And with that, maybe we take a short break. And I give it back to you, Morris.
Yeah, thank you very much, Chadi. Excellent. And I hope all of you here from the students have also realized how it nicely connects back now to material we had in earlier lectures. One of it is, of course, the machine learning library that you see here, where we had logistic regression in the beginning of the course, and let's say another algorithm in the realm of machine learning. But it also provides you here a scalable solution for the FP growth algorithm. You can consider also what Chadi has said, that, of course, the shopping data often accumulates over years and maybe even decades for large shops. So you're really confronted with large quantities of data. And then with Apache Spark, you have a scalable solution in the cloud that really can tackle these sort of problems. And of course, similar solutions, as you know, not only HT Insight provides Spark, we have also seen now AWS and Google Cloud are also providing Apache Spark. So of course, similar things are also then absolutely possible in all the different hyperscalers, really. So in this sense, I think it connects nicely back to this lectures we had earlier. And let's take maybe just 5 minutes break, and then we can come back to the next part of the lecture.